And I hope the chair will manage to connect. And yeah, I can introduce myself. I'm Daniele Fausti, and I work from those two institutions in the picture, like the University of Trieste and the synchrotron and free electron laser facility. And I thank the organizers for inviting me, and apologize for the technical inconvenience we're having. So I'll just move on the presentation, and I'll try to be on time. Just ask me questions anytime. Hopefully I will see them if the chair cannot interrupt. Okay, so the presentation I will give is just to introduce a little bit what's interesting to us, and mainly how do we control the optical properties, how do we control the physical properties of complex materials through irradiation. And after talking to Elisabetta, I decided also to put a little bit of the latest direction which we're trying to follow to address our problem. So the talk will be in the first part where I will show you what's been done and what's interesting to us in this respect. And in the second part, I will just show you some new analytical tools that we developed, mostly regarding studying optical correlations. So before starting, I have to acknowledge the people who actually did the work, and I'll present different projects, mostly done by the people highlighted in bold here, and the main project will be the project of Francesca Giusti, Angela Montanaro, and Filippo Glerian, and some former members of my group, George Sparapassi, more than the central figure here, and the theory is done for one project in the group of Shaul Mukamel, for the other project in the group of Fabio Benatti. So what's the idea that we are trying to pursue? Basically, we want to do non-equilibrium physics in complex material. And why do we want to do this? Well, the general idea is that, first of all, I'll give you a very personal perspective, in the sense that in these slides, I will cite only my own work, which is not representative of the whole field, but I'll just give a snapshot of what I think is the interesting problems that are open in the field. First of all, the idea is that we study non-equilibrium physics to understand equilibrium. And the idea here is that we want to use, so we are interested in those materials where the interplay between the different constituents of matter give rise to peculiar physical properties in the system. And the idea of non-equilibrium studies is that we can try to understand how these different constituents talk to each other and how do they determine the physical property of the material. And one famous phase diagram is this phase diagram of high temperature superconductor, where by just changing a little bit some parameter like temperature, pressure, or doping, you can switch from insulating behavior to superconducting behavior. So the system is very prone to any sort of instability. And why do we do non-equilibrium physics on those? Well, the idea is that if all the constituents of matter are talking to each other in a complex, intricate way, like you would, for instance, if you want to picture it like a bundle of different degrees of freedom, the idea of our study is to take one of these degrees of freedom out of equilibrium, and by looking at the relaxation process, we want to learn something about equilibrium. On the other hand, we want to do non-equilibrium physics also per se, in the sense that we want to study non-equilibrium physics to try to control the physical property on ultra-short time scale. And what is the rationale here is basically you start from the same phase diagrams, and this phase diagram, as I told you, allow you to think about those systems as if they are always on the verge of a massive change of their physical properties, and you can think of using light as an additional control parameter to obtain new functionalities which you do not have at equilibrium. And so you can think about these phase diagrams adding one dimension, which is actually the dimension of photoexcitations, and in this way you can obtain transient physical properties which you do not have at equilibrium. So that's been done a lot, and it's a relatively large niche of research, And one example, for instance, is a set of studies where we have shown that you could trigger a metallic state by photoexciting an insulator. And the idea here is that if you dump a lot of energy into an insulating material, these studies were done on the Vervey transition magnetites, you can actually, if the amount of light that you use is high enough, you can develop a metallic phase, and we could study the nucleation process of the metallic phase. This is a relatively trivial example in the sense that you do photoexcitation, and the photoexcitation results in a highly disordered state, which is the metallic state. And you can, and this is exactly what would happen if you just turn on the temperature. So if you just give disorder to the system. On the other hand, with the electric field, you can do something else. And in those studies, which are now a little bit dated, but in those studies, we could show that it is also possible with an electric field to trigger the formation of a superconducting state. And this is a little bit at odds with our intuition about thermodynamics, because what the light does, it generally drops energy into the material, but rather than inducing a disordered system, it triggers the formation of a low entropy phase. So clearly the electric field is doing something else. It's not just leaving energy into the system. And if you think about it, the situation is kind of counterintuitive, because if I want to recast this example with my bundle metaphor, it basically means that I start from a very disordered interaction between all the constituents of matter, and by photoexcitation I get a nice pullover. And this is actually, it's a very lively research field in the sense that how does the electric field trigger the formation of a low entropy state? And here I cite only my own works, but there's many other, and it's a quite lively research field. The common ingredient to all those attempts to drive order into matter are based on far infrared excitation. So just exciting with long wavelength pulses so that you can think of driving strong currents into the material, and by doing so, you can sort of trigger some dynamics without actually giving it too much entropy. And one of the key crucial concepts is the concept of the Phonon pump, where you resonantly drive vibrational modes. And one example in this, which I want to give a little bit more details, has been published a few weeks ago. It's from my group. It's an idea where we want to use the Phonon pump to control electronic excitation. So can we just drive a material response remaining in the electronic ground state so that we don't give thermal disorder to the system? And can we control the electronic excitation just by driving the structure? So in some sense, I like to give this example like as in the example of David and Goliath, because you want to use a weak interaction, which is the electron-phonon interaction, to control a strong interaction, which is the interactions between the electrons. And the system which we choose to study to prove that this is possible, it's one of the cuprates, so a system which is characterized by having some specific absorption in the visible, and this absorption is associated to a localized charge redistribution on the copper ions. And those transitions should not be allowed optically, but they are actually allowed because they are interpreted as phonon-assisted transition. So it's an optical transition which in principle is forbidden by dipole selection rule, but it's observed in real measurement. And this is so because the transition, the electronic transition, is assisted by a phonon excitation. So the structure comes in to break the symmetry and makes this transition allowed. So the idea of this experiment was relatively simple, because we just said, okay, if I can really make an electronic transition allowed by photoexcitation, can I actually resonantly drive the structure so that I move the ions around? And will I be able, by doing this, to change the electronic absorption of one single atom? And it turns out that the results were more interesting than we expected, because if you photoexcite the system with high energy photons, basically you never win against the entropy. So what your photoexcitation does, it's always to increase the disorder. And if you increase the disorder, the thermal excitation of the structure, then you always increase the absorption of these electronic transition, which are phonon assisted. On the other hand, if you coherently drive the structure, as we have done in the electronic ground state, you can find regions of induced transparency. And basically, this is a new way or a new kind of interactions where you can have a coherent interactions between two different fields, one of which is the elastic field of the material. So it's the elastic field that actually makes the electronic excitation transparent. And actually, it's a first example that by resonantly drive the structure in the electronic ground state, you can trigger the formation of some order in the electrons in some sense, because you can freeze an absorption which was there due to the thermal excitation of the phonon, and you can actually control it coherently by controlling the elastic field in the material. But so this is a general research field, and the idea is that after I've shown you that mid-infrared excitation is one of the key to try to induce some order, I show you the purpose of my talk is to show you what's the next step in terms of what are the observable that we are missing to understand the dynamics of complex material. And actually, this fits well to the topic of this seminar, because what we've been doing in the last maybe 5 years is to try to develop a new class of spectroscopies where we don't use just mean value properties of light, but we use also fluctuations. So photon number fluctuations and multimode correlations. And I'll just try to convey the general message that using this kind of fluctuations is meaningful in spectroscopic terms. They carry information which you don't have in mean value measurement. So what is the idea? The general idea is quite simple. So whenever you do a non-equilibrium study, you photoexcite the material with one light pulse and you measure it with a second light pulse. What does it mean to measure? It means that I have in mind measuring the evolution of the material property, and which actually means that I average over all the volume that I excited, and at the same time, I usually average over many repetitions of the experiment. If I change the perspective and I try to look at the problem not from the material point of view, but from the light point of view, what am I actually measuring when I'm measuring a pump and probe? Well, I'm actually measuring operators which are just telling me what's the mean number of photons coming into the material and what's the mean number of photons coming out of the material. I make the ratio and I get the reflectivity. But if I look at the problem in this perspective, you see immediately that the situation is much more complicated, because the information that I measure on the optical pulse is just very limited, because I measure just the expectation value of one form of operator. While in principle, in the pulse, I have much more information. For instance, I can ask myself, do I have information which is spectroscopically relevant from the fluctuations of the number of photons? So for instance, if I measure the fluctuations, how it evolves as a function of pump and probe delay, does it carry an information which belongs to the material? So do I learn something about the material by measuring photon number fluctuations? And we have been doing it a lot in the past, and the general idea is that we may be able to map fluctuations which belong to the material, for instance, such as thermal fluctuations of the atomic position, into fluctuations which I can actually measure on the optical pulse. And I just give some reference here where you can go and look it up. But what's interesting is the fact that I can also have measure operators which are not recasted as photon number fluctuations, but any general kind of operators. And in the last part of the seminar, if I'll have time, I'll show you how do we do a full tomographic reconstruction of the state so that we can measure, in principle, the expectation values of operators of any form on the quantum state. And more than this, There's also some very interesting aspects, and this is going to be the central part of the seminar, on where I can use classical fluctuations of light to measure the response of the material, not only quantum fluctuations. And I will start by classical fluctuation just by reviewing a little bit one recent example of a work we did, and we will see whether we get to the quantum fluctuation in the end. But as we have lost a few minutes, probably we will not get to the quantum fluctuation at the end. Okay, so how do we use classical fluctuations for measuring the response of a material? Well, the idea, and here is the main message of my talk, is that whenever we measure the nonlinear signal, and generally we are interested in nonlinear signal in time domain spectroscopy, usually we struggle a lot to obtain a very stable laser source. And this is because the nonlinear signal is small. But on the other hand, I will argue that we need a very stable laser source only because we measure mean value. If we change the perspective and we measure something else, for instance, the first thing which we can measure is correlations between probability of having photons at different frequencies, then we can actually gain from the noise. And the noise can become the source of information. And I'll show you a very nice example which we recently published, where we use the noise as the source of information to gather information about the material. So what's the philosophy here? So basically, we just take pulses, which are very noisy, like, for instance, this is like the frequency content of one single light pulse, and the noisy animation is just different measurement, which I repeat pulse by pulse. So the idea is that I repeat many measurements with random fluctuations, and rather than measuring the mean value response, I measure what is the correlations between having a photon at one frequency and having a photon at another frequency. And this is quantified in this mathematical form, which I don't want to go into details, but just the correlation. How much the probability of having a photon at one frequency correlate to the probability of having a photon at another frequency. And these are simulations. What can I expect? For instance, this is a typical noise which you have on the laser, where your intensity fluctuates. And if you measure the correlation pulse by pulse, you get something which is like a red blob on this frequency axis. So this is the correlator as a function of frequency and frequency, how much the intensity fluctuations correlate. And if you have intensity fluctuation, you get this red blob, and it's relatively easy to understand why, because if you look at one single measurement, the gray line here is the average, the black line is the single measurement. If the single measurement is above the average at one frequency, it's above the average at all other frequencies. So the correlation is positive between all the frequency components of my sample. On the other hand, if I have, for instance, frequency fluctuations, what do I expect? Well, I expect to have like negative correlations between frequencies which are on one side and frequencies which are on the other side, because if for a given realization the frequency on the right are above the average, the frequency on the left are below the average. So I have these negative correlations between frequencies which are on the opposite side. And the most interesting situation instead is the situation where I have frequency uncorrelated fluctuations, so that one intensity correlates only with itself and it doesn't correlate with anything else. And why is this the most interesting situation? Well, the idea is quite simple, and this is the first experiment we did. We tried to measure some Raman scattering, as in the previous speaker. And if you do Raman scattering, what happens is that you destroy a photon at one given frequency, and you create a photon at a frequency which is moved with respect to the central frequency of the frequency of the phonon which actually mediated this scattering. And if you start from the situation where you have these frequency uncorrelated fluctuations, as I've shown you before, what can you expect? Well, I can expect that if for my pristine pulse I have correlations only with one frequency and itself, if I have a Raman process, then the two different the frequencies which differs of big omega, where big omega is the frequency of the phonon, they are no longer independent. Because if I destroy the photon at one frequency, it has to appear at another frequency. And this, of course, happens simultaneously on all the frequencies, so that I can expect to see correlations at frequencies which are associated to the frequency of the phonon modes. And here is the experiments I'm going to discuss. So, for instance, if I have like, we develop a laser source where we could introduce frequency uncorrelated noise, just with a pulse shaper, I spare you the detail, and then we do single shot measurement for these pulses, and we just acquire them like here. And the animation here is data, where I show that the spectral content of every single pulse is completely different, and the fluctuations are random as my random number generator. So every spectroscopist in the room will tell you that it's impossible to measure with this kind of laser. But if you look at the correlations, it seems exactly like the correlation that we wanted, because one frequency correlates only with itself, while there's no correlations between frequencies which are not which are different. This is the white spectrum here. Now I use the same set of data, which I split by a beam splitter. I make them interact with a sample, and you see immediately that again, I don't see much if I look at the pulses, because I do have random fluctuations. But if I do the correlations, I see that immediately I develop correlations which actually correspond to the Raman response of my material. So I introduce correlations between frequencies who differs of the Raman mode of the material. And this is actually a very interesting, here is the reference, it's a very interesting spectroscopy, because what you can do, you can have a Raman response, which is measured on a time scale, which is as short as your light pulse, but on the other hand, with a frequency resolution, which is just determined by how large is your frequency correlation here. And you can do more, this is a bit of detail, but I can actually imprint the fluctuations only on one part of the spectra and leave the other part with coherent fluctuations. And if I do the correlator, I have a correlator where all the frequencies here are highly correlated, all the frequencies here are uncorrelated. And if I measure the Raman response, I see basically that I can measure even very weakly scattering phonons. It's a relatively sensitive technique where you can actually address the frequency of your modes on ultra short time scales. And okay, so how do we want to use it in time domain? And this is like Elisabetta, how much time do I have? Can you speak, or Elisabetta?
Can you hear me?
Yeah, now I can hear. How much time do I have? Because we also started late, right?
Maybe no. Yeah, you run out of time now, but we start late, so I guess a couple of minutes.
Okay, let me close it up then. So basically, now what I can do, I just skip all the central part, but basically, what I can do now, I can trigger some time domain response, so I can use this technique coupled to an optical pump, which actually triggers some coherent response of vibrational mode. And I can study the scattering process as a function of time. Here, the times evolve in this picture, if it evolves, yeah? And here it's a correlation between a scattering process which is of Stokes nature versus a scattering process which is of anti-Stokes nature. And you see that actually I can measure the evolution of this correlation, and the Stokes process and the anti-Stokes process are in anti-phase. So whenever the phonon mediates a scattering process which reduces the energy of the photon, it does so, but with the opposite sign, to increase the frequency of the photon. So the correlation reduces towards high frequency when it increases at low frequency, and vice versa. So the idea is that we we could use this to do a full statistical distributions of the phonon mode. And the last part of the seminar was just try to focus on how do we push this towards the using quantum fluctuations, and we have developed a technique for measuring multi-mode correlations with a few photons per pulse. And actually, we have some evidence that it may be we may have correlations also at the quantum level as we did classically, and this would be pretty interesting to try to to measure the intrinsic fluctuation properties of the atomic position, and so the fluctuations of the elastic field, just by measuring how the atoms move into the potential and how strong is the potentials around the atoms, just by measuring the fluctuations that they have in a dynamical response. Yeah, I'm sorry I've been cutting it a bit short, but I think we can conclude here, and this is what.
Thank you.
What I think it's an interesting direction to go.
Thank you very much. I still apologize for the inconvenience at the beginning. Now I am in a very provisional situation. So, is there any? Let me first thanks Daniele for this very interesting talk. Actually, it is very interesting to shift the point of view, right? Rather than looking from what the light can do to the material, what the material actually does to light, and this is a very interesting point, and also to develop new strategies, as you were showing us. Let me check the chats if there are questions for you. Okay, serious questions. Sorry, I still have to take confidence with this system. There is a question, yes, is it a wavelet analysis shown on this picture?
Sorry, I didn't. Is it a wavelet analysis?
Shown on this picture.
The picture here? No, actually, this is the part I didn't see. No, this is basically the measurement of the. So this is like a coherent phonon measurement, but where I measure not only the intensity of my field, but the amplitude of the field and the phase of the field, just through this heterodyne description, which I haven't detailed here. And basically, the interesting bit is that if you measure also the phase, you see that while in the amplitude response, you do have an anti-phase response between the frequencies which are on the blue side of the pulse and on the red side of the pulse, like you expect in impulsive stimulated Raman scattering. The phase response instead is the same for all the frequency components. So this is not wavelet analysis, but this is just simply like a time evolution and the amplitude of the response and the phase of the response for all the different frequency components. So it's not a wavelet analysis, but basically it's the different frequency component of the pulse. How do they evolve as a function of time?
Thanks. And there is also a question about, I think we have a few minutes, about what we are doing actually in COPAC, right? So the question is, in COPAC we are working with size disorder quantum dot. So can we reverse your argument and probe the disorder of the sample?
Okay, this is a good question. So basically, you are saying if I have a quantum dot which have spectral response which is different, and I have an heterogeneous ensemble of quantum dots, will I be able to distinguish what's how heterogeneous my solution is? It's a very good point. I'll be happy to discuss. I don't know, in the sense that if the scattering process will be mediated by only one quantum dot, so in principle it should contain an information which is specific of the quantum dot. So in principle, this information in single shot correlation measurement should be there, but people would need to think about how to do it. I'll be happy to discuss if anybody is interested.
Yeah, I mean, we will be very happy if you can join the roundtable at 5:10 in the afternoon if you have time, if you can.
Yeah.
Or maybe the roundtable tomorrow, right? Because this is a very interesting point. We have a lot of yes from the other people of the consortium. So, I mean, we will be happy to discuss more about that. If I still have time, there is another question about if there is any. Can there be a time domain version of the fluctuation spectroscopy where the sample dynamics can be observed?
I'm not sure I understood. Do I also read the question, or?
Yes, you can go to the chat.
Can there be time domain version of the fluctuations where the observed dynamic can also be observed? Yeah, exactly. So this is what I actually showed. Let me just go back to the slide. So it's unpublished. So, but basically here it's this fluctuation correlation spectroscopy as a function of time. So this is an experiment where we did some photoexcitation with a short pulse and some correlation measurement, as I showed you in the talk, just by measuring the single shot correlations. And all those lines that you see here, this corresponds to the phonon modes. And you can shape your pulse so that you select only scattering process, which are from high energy to low energy, as you see on the left, and from low energy to high energy, as you see on the right. And you see that if you do the experiment at the same time, you see that basically the lines associated to the same phonon, they oscillate in anti-phase. So you can see the coherent response of the phonon, and you can see the evolution of the momentum of the motion of the phonons in this respect. How to deconvolve the statistics is a subject that we are working on now with the group of Shaul Mukamen, and I don't have a specific answer yet, but you can measure this fluctuation spectroscopy with the time resolution, and you have a time resolution which is as short as your pulse, but a frequency resolution which is as good as the width of one of your spike in this. It's a little bit like femtosecond Raman spectroscopy, where you have like a narrow band excitation and a broadband one, and the time resolution is given by the broadband and the frequency resolution by the narrow band. But it's much simpler than femtosecond Raman.
Thank you very much, Daniele, for sharing with us this very, new, I understand.
Yeah, this part is new. This is like, we are working on it now. We have a draft, but we are working on this now, so it will come out soon.
Yeah, thank you very much. The audience was very interested, right? So if you can really join us in the roundtable later, we will be very happy to discuss more on this.
Sure. No, I'll be happy.
Thank you very much. And thanks also for staying in time, perfect time. And so it is now time, I guess, to move to the poster session room. And so let me thank again Daniele for this very nice talk. And I'll see you all in the poster session room. Thank you very much, Daniele.
Yeah, grazie Elisabetta.
Grazie, ciao.
Bye.
Scusa per la confusione.
No worries. Bye.
Ok. Bye.
Bye.
Ok.